Okay, good morning. So let's start the last day of our school. Yes, the last day. So I'm already missing this wonderful school. So let's continue. And the next lecture will be given by Dr. David Catling.
David, would you like to turn the lights off for
Yeah.
a better view?
Okay. So today I'm going to talk about detecting planets which have life on them remotely. So this is a picture of the Earth. This is actually stray light, so it's not real, the rest of this mess here. But this is the Earth in a pixel, and we see its color, which is a pale blue color, which results from the Earth's atmosphere. It's a clear atmosphere, transparent to sunlight, but it scatters a lot in the blue by Rayleigh scattering, the same process that gives the sky its color, the daytime sky's color. And the combination of the clouds and the Rayleigh scattering makes this pale blue dot. But it does actually encode a lot of information about the atmosphere. The fact that it's transparent means it's oxidizing because it gets rid, the oxygen gets rid of the organic compounds in the atmosphere. And also the rain, it's wet, so the rain clears the atmosphere. And these things are connected to the habitability of the Earth. So this lecture has three parts. First of all, I'm going to talk about the habitable zone, which is the region around a star where a planet is likely to have liquid water on the surface. And what defines that habitable zone, and also people's questions about whether the habitable zone is the right concept, or should there be a different concept. Then I'll mention a few principles regarding spectra, because what we want to do is to split up the light from a planet. So instead of having a pale blue dot, we have the reflection, for example, over a range of wavelengths. Should it be the infrared or the visible or the ultraviolet? Those are all questions. And then I'm going to talk about biosignatures, which are distinctive signals that indicate the presence of life on a planet. And so we can consider Earth. We can consider the concept that chemical disequilibrium in an atmosphere results from large biological fluxes of gases that are incompatible if it were just an abiotic planet, which would come to some kind of boring equilibrium. And we can also consider the issue of, should we look in the visible at a planet or the infrared for these biosignatures? So the first part, the circumstellar habitable zone. So this has a long history that goes back to the 19th century. This Cambridge University professor talked about a zone around a star, and it was he used the words a torrid interior and a frigid exterior where life couldn't exist, but in between there was a belt where you could have liquid water. And later on, Harlow Shapley, an American scientist who discovered the dimensions of the Milky Way, also talked in his books about a liquid water belt around stars where planets would be habitable. But people didn't really try to put numbers on where this habitable zone was until the 1970s, when a scientist working on a NASA project, Michael Hart, tried to estimate where exactly the habitable zone is, so the distances where it's too hot and where it's too cold, the limits to this habitable zone. And then today we define the habitable zone as the region around a star in which an Earth-like planet could sustain liquid water on its surface at some instant in time. So it's defined as an instant in time because stars evolve, their luminosity increases over time, so we have to talk about when. But there's also this term, a continuously habitable zone, which is the region where a planet could remain habitable for some defined length of time. And the defined length of time is usually taken as the main sequence lifetime of a star. So when it's in its stable, relatively stable phase of fusing hydrogen into helium, like the sun is a middle-aged star in its main sequence. And when Michael Hart did this calculation, he had a very narrow habitable zone, where on the interior, a planet would have a runaway greenhouse, and on the exterior, a runaway glaciation. And he concluded from this that Earth, just by luck, was a habitable planet. But when you look at his calculations, this result is embedded in his assumptions. And his assumptions are now considered to be incorrect and unduly pessimistic. So there are other calculations since then that have been done. We could, of course, guess from our own solar system limits of habitability, where it's too hot and where it's too cold. And we could look and say, well, Venus is at 0.7 astronomical units, it's clearly uninhabited, so that's at least probably something to do with an inner edge. We could look at Mars, which currently is dead on its surface, at least, and we could say, well, that's at 1.5 astronomical units, so maybe it's somewhere between those two limits, at least in our own solar system. But where Michael Hart was right is that it's still agreed that the inner edge is determined by loss of water from the runaway greenhouse effect as being a good boundary. So if you have a planet which has enough liquid water, has an ocean, if you put it too close to its star, then theory says that it should undergo this runaway greenhouse effect that I talked about earlier. What defines the outer edge is built on some assumptions. So if we assume that it's a liquid water planet and that it also has carbon dioxide, then there's a problem, which is if you go too far from the star, the atmosphere becomes so cold that the carbon dioxide begins to condense into clouds in the atmosphere, and it's no longer a greenhouse, effective greenhouse gas once it forms a condensate, and actually if the particles start falling to the surface, then you lose the greenhouse warming. And so this is how people define the outer edge. But some people consider these limits too restrictive. So for example, on the inner edge, imagine a planet which doesn't have an ocean like the Earth, but just has a few lakes. Maybe like the lagoon here in Rio, a few of those. Well, it doesn't have enough water to undergo a runaway greenhouse effect. So one could imagine a fairly dry world, but with pockets of water that might not obey this limit. And then for the outer limit, well, maybe the assumption of carbon dioxide is too Earth-centric. Imagine other atmospheres that are stuffed with other greenhouse gases. If you have a lot of hydrogen, that can behave as a greenhouse gas, or a lot of methane perhaps, or some other combination of gases, not just CO2. Just to remind you, I had this on a previous lecture. This is the Earth, and this is an intermediate stage where it hasn't quite gone runaway. Early Venus, what we call the moist greenhouse, where it's a very wet atmosphere, but it hasn't reached the point where the outgoing thermal radiation is limited, capped to a value for the Earth about 300 watts per square meter. This is what happens when you reach the runaway. Everything evaporates into the atmosphere and the surface melts. So in fact, another nuance is that planets could be in what's called this moist greenhouse phase for a certain period of time. So early Venus might have been like this. It might have potentially been habitable for some time before the sun got brighter and it inevitably got into a runaway greenhouse effect. So you can think of the inner edge of the habitable zone as being a bit fuzzy because of this transition state to the runaway. But there is some evidence that Venus did have a runaway greenhouse effect. Some people cite the D/H ratio, which is about 100 times bigger than the Earth. But of course that could have been set in recent history. But nonetheless, we look at Venus today and we imagine that it had a similar inventory of water, and there was some transition here which theory predicts was the runaway. If we look in more detail to some calculations, this is the solar flux relative to present Earth, which is unity. So this is 20% more solar flux, 40%. Present Venus is almost twice as much flux from the Sun as the Earth. And this is early Venus. Early Venus was about here because the Sun was fainter, and it's right on the edge. So this solid line maps to this axis, surface temperature. The dashed line is water vapor abundance in the stratosphere, which is related to the runaway greenhouse effect. So this is the mixing ratio of H2O. So this is saturated when it means all of the gas is water vapor at unity. And as you heat up a planet, as the solar flux increases, more and more the atmosphere becomes saturated, and then it reaches the runaway greenhouse limit at this point here. And the surface temperature goes up to the melting temperature of rocks. So Venus was doomed to be uninhabitable, but whether, because it's on the edge, it may have been habitable right at the beginning. And the estimates for the runaway greenhouse from these calculations is that the solar flux needs to be about where this transition line is, so that's about 1.4 times the present solar flux, or equivalently 0.85 astronomical units. Or the moist greenhouse, this transitional state, happens a bit earlier, 0.95 astronomical units. There are differences in some recent papers on these exact numbers, but from my point of view, I don't really care that much because there's slop in the calculations. And the slop comes about because of clouds. Clouds can reflect the sunlight, so they can delay the onset of the runaway greenhouse. And it's hard to know the exact effects of clouds. So if somebody publishes 0.97 instead of 0.95, and they think it's assigned some magical value to that number, then they're really ignoring the uncertainties in clouds in these climate calculations. And that's the caveats. I've just said all this, and this is actually for a 1D climate model, so that's another caveat. In 3 dimensions, we know that there's circulation of the air, and the circulation can also change the albedo as a function of latitude, and there's another nuance that could be taken into account. And for the outer edge, there's this assumption about how the greenhouse effect works and what the greenhouse gases are. We also go for the continuously habitable zone. There are biogeochemical feedbacks or geochemical feedbacks that operate to keep a planet habitable. So earlier in my lectures, I mentioned the carbonate-silicate cycle. And this is like a thermostat in a room which keeps a good temperature by regulating the amount of carbon dioxide in the atmosphere. If it's too hot, it goes out by weathering. If it's too cold, it builds up by outgassing. And this is very effective for the Earth over time scales of a million years, which is short geologically. So when we put this all together then, we have an outer edge somewhere inside the orbit of Mars to outside the orbit of Mars. You may say, well, this doesn't make sense because Mars looks like an uninhabited planet today. But Mars is partly an uninhabited planet, not because of its position, but because of its size, so that it lacks this. There are no active volcanoes on Mars. They're all extinct volcanoes. doesn't have this way to recycle CO2, so it has a thin atmosphere, and because of its size, it's also lost the air. So maybe if you had an Earth-sized planet at the position of Mars, maybe it would be habitable today. We just didn't have that in our particular solar system. And this uncertainty is again due to the way this is set by carbon dioxide condensation. There's some uncertainty in how that behaves. So there's a spread here. So the habitable zone around the Sun looks like this, roughly speaking. And the Earth's orbit is pretty close in this conventional view to the inner edge of the habitable zone. But fortunately, it's been in the continuously habitable because despite the increase in the solar luminosity with time, it's able to regulate the atmosphere and change its greenhouse effect through the carbonate silicate cycle. Now this plot shows the continuously habitable zone. So Earth has been in it for a while, but if we go further in the future, as the Sun warms up, in theory, the Earth should eventually hit a point where, this is not showing on the screen here, but there's actually some other bounds. Can't see it here. There's some other bounds here which are, so this is conservative, and there's some other bounds which are wider. So if you take the wider one, then in a few billion years' times, the Earth will hit a runaway greenhouse effect. Between that time and now, it might go into what we call the moist greenhouse effect, the intermediate stage. But it doesn't matter, because eventually the Earth has this to look forward to. So in 4 billion years' time, even in the less conservative estimate, the Sun is so powerful at that point that the Earth should go into a runaway greenhouse, and these ocean should all evaporate, and the surface should melt. This is an artist's impression. But of course, we can apply this principle to other stars. So if we go to the most famous diagram in astronomy, temperature runs backwards from hot to cold to match these spectral types. And then up here is luminosity relative to the Sun, which is unity. Here's the Sun here. And when we consider habitable planets, we usually ignore things that might be around these O, B, or A stars. And there are a couple of reasons for that, which would be what? Bearing in mind some guidelines here. One reason, of course, is lifetime, which is these stars are very young, and so, well, we don't know how long it takes for life to originate and develop, but these seem like a bad idea because they live for such short amount of time. And then, secondly, these stars have very intense ultraviolet and could drive. There are other issues, so atmospheres are more prone to escape, even if you're in a habitable zone. So we're usually thinking about stars like our own, the G stars, maybe some F stars, K stars, and M stars, the habitable planets. And of course, the habitable zone will move inwards for a cooler star. So here it is for a mid-K star, and here it is for a mid-M star. And when you get to the M stars, then it's so close that you have another issue, which is that one side of the planet will face the star, because of the gravity locks it into that arrangement, just like the moon always faces one side to the Earth. So there's a tidal lock radius, which is marked by this dashed line here. And as you go to the M stars, that goes in. And it's just like this moon going around us, where one side marked here, we put a little mountain on the moon. This is just a schematic diagram. Here's a lunar peak, and it's always facing the Earth. So the question arose back over 10 years ago, would a tidally locked planet be uninhabitable? Because this is the day side, and there's a permanent night side. Could an atmosphere condense out on the night side and make this uninhabitable? And initially, some papers, I think in the 1980s or 1990s, just made this statement, well, these wouldn't be very good for habitability because their atmosphere would condense out. But then people started to do three-dimensional climate models and showed that even with a moderately thick atmosphere, certainly comparable to the Earth, what happens at this subsolar point is that it causes a big Hadley-like circulation, like a Hadley cell, and that can transport the heat enough to the night side. And if you have a liquid ocean here too, that can also transport the heat. So the atmosphere doesn't freeze out if it's even a fraction, of maybe a few tenths of the Earth's atmosphere, something like that. But in fact, we have that information already. When we look at Titan, which is tidally locked, and when we look at Venus, which is a very slow rotating planet, we find that actually the surface temperature on those bodies is very even because they're very efficient at transporting the heat through their thick atmospheres. So the temperature difference between the equator and pole on Titan is 94 Kelvin at the equator and 90 Kelvin at the pole. And on Venus, there's about 4 or 5 degrees difference. So there's no problem in being tidally locked. And maybe this is fun for people, for aliens living on these planets. You know, they can always go to a nightclub just around the other side, permanent nightclubs. And if you're on the Terminator, that would be the best place to live. But, as I said, the conventional habitable zone concept of inner edge, runaway greenhouse, outer edge, condensing carbon dioxide, may be too conservative. So this is from Sarah Seeger's paper in Science last year. And let's see, the light blue is the conventional habitable zone. And this green-yellow is for these dry planets that just have lakes and more difficult to undergo a runaway greenhouse. And the blue extends all the way out to the outer solar system because she argued you could have greenhouse effects caused by things like hydrogen or methane that could extend the habitable zone out into these regions. I think these are exoplanets plotted here. So there's some uncertainty as to what exactly is the edge of the habitable zone, and probably we should keep an open mind. However, I would say that if you're making your greenhouse with hydrogen, which is a good greenhouse gas in a thick atmosphere because of collision-induced absorption, these collisions that cause distortions of the electronic cloud in the molecule and a temporary dipole, allowing this, what is a non-polar molecule, to become polar. Remember, this is food for microbes. So if you find a lot of hydrogen and nobody's eating it, that's not so good for an inhabited planet. It means no one's home. Remember the analogy, you leave a pizza in the university hallway, it doesn't get eaten, no students, no life. You leave a lot of hydrogen in an atmosphere, nobody's eating it, probably no one's home. Provided there's some oxygen. And if you find an oxygen and hydrogen, nobody's using that, then that's like an anti-biosignature. So, to summarize on the habitable zone around F, G, and K stars are relatively wide, and some argue they're even wider. And these are long-lived stars, in the case of G, similar to our own, that potentially could have planets with life. Stars hotter than the F0 stars are probably bad candidates because of their short lifetimes. M stars have very long lifetimes, and so good continuously habitable zones in principle. They have tidal locking, which is not a problem if you have a thick atmosphere. But there may be other problems with M-star planets, which I won't go into. So the next part is thinking about how if we choose our planet in a habitable zone, how we look for the signs of life remotely. And I showed you the picture of a pale blue dot, the Earth, viewed from a distance. And here it is again. And we could guess that maybe this color is caused by a mix of blue oceans and Rayleigh scattering air, whiteness from clouds. But there are other blue planets in our solar system, such as Uranus. So how can we do better? Well, the answer is to see the difference between an Earth and a Uranus, you need a spectrum, because this integrated color is not enough. You need to see the way that the light splits up, and then you can start to diagnose the differences. So Uranus, for example, is blue because the methane absorbs in the red, and so which you don't see for the Earth. Earth is blue because of the Rayleigh scattering of the atmosphere primarily. So this is just a reminder of some basic principles of emission and absorption spectra. If you have a hot gas, you'll see emission lines, and if you have a cold gas and the light is going through the cold gas and gets absorbed, then you'll see absorption lines. And in planetary atmosphere spectra, actually, you can see both. Sometimes if the atmosphere has a hot area like a stratosphere relative to a colder area below, a troposphere, then sometimes you can see emission lines coming from stratosphere, and you'll see absorption lines for other parts of the atmosphere. And here are some spectra. This is in the infrared, going from 5 microns to 30 microns. And these are from some planets, solar system planets. You can probably guess which ones are which. The colors are meant to make you guess. So this is Venus, and we can tell that there's carbon dioxide and sulfur dioxide in the atmosphere, so there are some sulfur dioxide absorption lines. Earth is different because of many water absorption lines, which is causing all of this fuzzy stuff on this spectrum. And Mars is dry but full of CO2. And so you can begin to see some differences. And if you look in the visible and near infrared, then it becomes a lot clearer actually for the Earth, where we begin to see other lines like oxygen, molecular oxygen in the visible, many water lines, and then a rather boring spectrum for Mars, but we see iron oxide absorption. So we see the surface here, and we see a lot of CO2 lines for Venus. So we could ask the question, should we look in the infrared like this, or should we look in the visible near infrared, which is this part? And there are practical reasons to consider when you think about either of those. And I'm going to talk about, this was a NASA concept. It still is a NASA concept, but it's not a mission, it's an idea called Terrestrial Planet Finder. The idea is to look for spectra from Earth-like planets. And if you look at the photons, the flux, you'll see that there's a contrast ratio between a sun-like star and the emission from an Earth-like planet, which in the visible is about 10 to the 10. But in the thermal infrared, it's much better. It's about 10 to the 7. So that's these lines here. So you might think, well, okay, so it's a lot better. This is going to be much easier to look at the thermal infrared, to ignore the stellar output, which of course is much larger. But there's another factor here, which is that your angular resolution is set by diffraction, which is the wavelength over the aperture of the telescope. And actually, this is smaller for the visible and bigger in the infrared when you run through these numbers. So if you're going to build a telescope, you need a smaller one in the visible, a bigger one in the infrared. Well, this may or may not be a problem, but the way it's been thought of is that you use something to block out the star called a coronagraph in the visible, and in the infrared you'll use interferometry techniques to null out a star in the starlight in the infrared. Both of these are very complicated technologically and for the future. If we look at the infrared spectrum, this is wavelength in microns, and here's Venus, Earth, and Mars, again, on the same plot. And what's particularly diagnostic here, at least in the infrared, is the ozone feature, indicating molecular oxygen. And then all the water features indicating a wet planet. We also, if you want to know there's liquid water on the surface, you need to know the surface temperature. And the surface temperature depends on the nature of the atmosphere and the greenhouse effect, and whether you can see the spectrum, whether you can see in the spectrum the actual surface, which is an issue. These are the equilibrium temperatures for airless bodies, everything else being equal, the albedo, and assuming it's isothermal. And this is the actual surface temperature, and then this is the greenhouse effect. So the greenhouse effect is at least as important in determining a surface planet temperature as the distance from the star. And the Earth's atmosphere is cooperative. This was a plot we had earlier, so this is wavelength, and this is relative energy intensity. And we saw that the Earth has a window where we could see directly the light emitted from the surface and diagnose the surface temperature. But if we try that for another planet in our solar system, Venus, we just see in this wavelength range the emission from high up in the atmosphere where it's much colder than the surface. So if we were to look at this spectrum, how do we know the surface of Venus? What temperature is it? All we're seeing is emission. Because it's so optically thick, we can't see the surface. All the infrared photons are absorbed, emitted, absorbed, emitted, and finally it becomes optically thin at temperatures of 250 Kelvin up here, or even in the CO2 band, which is even more optically thick, we're seeing temperatures which are down here at 180 Kelvin. So we can't see the surface. So if we had this for an exoplanet, it would be difficult. We might make a mistake and think, oh, maybe we're seeing a window, but we're not. Or we would be intelligent and we would realize we're just seeing the atmosphere, and we'd say, we don't know the surface temperature. But that's something we really want to know, because we want to know if it's within the range of liquid water, because that's our definition of conventional habitability. So that's the problem. In Venus's infrared spectrum, photons are only seen emanating from colder, higher parts of the atmosphere, none directly from the hot surface. So what we have to do in those cases is we can measure the atmospheric composition and have a model and try to infer the surface temperature from the model, but that's not very necessarily convincing, because you may not know the composition well enough for your model. On the other hand, you may be lucky, there may be an atmospheric window, you may be able to see the surface. And you can see deeper in Venus's atmosphere, we know from looking in the near-infrared, which is how astronomers look at the surface of Venus, or the deep layers of the atmosphere in our solar system. So part 4.2, biosignatures. This is the third part of the talk. And there's been a sort of look at the Earth, which is a dry run. In other words, a kind of trial run for exoplanet searches. And it was done by the Galileo spacecraft. So the Galileo spacecraft had to do a gravity assist, or more than one gravity assist, to get to Jupiter. And in this pathway, it looked back at the Earth, and the instruments took spectra of the Earth. And this is the paper published in 1993, A Search for Life on Earth, from the Galileo spacecraft. Of course, we know life exists on Earth, so you may think, why did this paper get published in Nature? But the idea was that this would demonstrate some of the principles for looking for life on other planets as a control experiment. So what did they find? In the near-infrared, many water vapor lines, and also oxygen absorption at 760 nanometers. So immediately you could infer a wet planet, and you could infer one with a lot of oxygen in its atmosphere. And oxygen in abundance is usually, could be attributed to life. Also, in the near-infrared, other gases, methane, 3.3 microns. This is the same notorious 3.3 microns for the Martian methane, detected remotely, allegedly. And then more water vapor lines, and then nitrous oxide. Nitrous oxide today is produced by biology in the part of the nitrogen cycle called denitrification, where nitrogen is put back in the air, mostly as N2, but a fraction comes out from the biology as nitrous oxide. Ozone. So now we have several biogenic gases. We've got oxygen before, also inferred from ozone. We've got nitrous oxide, so that's 3 of them, and ozone, of course, comes from oxygen. So oxygen, O3, sort of together are biogenic gas. Because you've got a lot of methane and oxygen together, those things should react. They react through a series of chemical processes, but the net reaction is like combustion. Let me see, does that balance? No. So the atmosphere is like an engine, and the spark plugs are given by ultraviolet radiation. It causes a lot of chemical reactions, but the net reaction, the overall effect, is that the methane should react with the oxygen and disappear. And it's out of equilibrium by a factor of 10 to the power of something like 145, something like that. So a big number, that is disequilibrium. What it means is that you can maintain a disequilibrium if there are big fluxes of the oxygen and of the methane. What could cause those big fluxes? Well, you could have methane from volcanic sources, oxygen, much more difficult without biology. And the two together suggests an active biosphere. This idea was originally suggested by Joshua Lederberg, a Nobel Prize winner in bacterial genetics, and James Lovelock, an atmospheric chemist. In 1965, there were two papers in the same volume of Nature saying, if we want to look for a biosphere, we look for chemical disequilibrium, because it shows that there are big fluxes of chemicals that should, if it were a dead planet, react together and not be there. And oxygen and methane are, in a sense, a robust biosignature. So here's the photosynthesis for oxygen, and here's methane made from organics. This is a rice paddy. So there's microbes in here which are in these anoxic sediments which are making a lot of methane by decomposing organic matter. But there's a problem. All planetary atmospheres are in disequilibrium to some extent. So the input of free energy, meaning energy that's available to do work, happens for all planets, because it's receiving a planet receives free energy from sunlight, and that breaks up molecules and creates some temporary disequilibrium continuously. So if you look carefully, in every atmosphere, you'll find some disequilibrium. So it's a question of degree, how much? And you could also ask, what about the anti-biosignatures? They could be a lot of disequilibrium when nobody's using it. Okay, the no one home idea of seeing a lot of hydrogen or a lot of carbon monoxide. So there are some nuances in this basic idea. If you do some calculations for our own solar system, you can see the differences in disequilibrium. So I've done some of that, but I haven't actually published it except in conference abstracts, but here it is anyway. So this is the change in Gibbs free energy if you take a mole of air on one of these planets and you react everything to chemical equilibrium. How much energy do you get? So that'll be joules per mole here. And what's underneath the RT is just the thermal energy, which I've normalized to, because planets close to the sun get more energy, free energy from the sun, so I wanted to try to normalize for that. This is a little arbitrary, but I just stuck RT in there, and then you get a non-dimensional number. And so here it is for the Earth, Mars, Titan, Venus, Jupiter. And the Earth stands out by orders of magnitude. Mars has quite a bit of chemical disequilibrium just caused by sunlight, which breaks up the carbon dioxide and makes carbon monoxide and oxygen. Those two things exist in disequilibrium in the Martian atmosphere, but it's a small disequilibrium just caused by sunlight. But the Earth is unusual because its atmospheric chemical free energy is much bigger than its thermal energy. And it's the only one in our solar system that's like that. Now it's like that largely because there's a lot of oxygen. And I want to try to do this calculation for the Archean Earth, and it may not work so well. The Earth is going to drop down somewhere. Maybe this is no longer satisfied. But at least for a modern oxygenic Earth, it stands out. Yes?
It's an extremum, but it doesn't, to me, stand out, because Mars is closer to Earth than it is to Venus.
Yes.
So,
because of it has the carbon monoxide.
absolutely, but just, we have 3 of these bodies. Forget Jupiter, I mean, that's more extreme, but that's a very different type planet.
Well, Venus is so hot, so this is for the lower atmosphere, so Venus is so hot and high pressure that it's pretty close to chemical equilibrium. And so that's why these 2 planets are down here.
But just, we only have a few samples, and the range of the non-living is pretty big. If you just had 100 non-living planets, I wouldn't be surprised if one would be bigger than Earth.
Maybe, but nobody knows the composition of these hypothetical planets.
Of course.
I'm just using real data and showing you the differences.
Yes.
And that's all I can do.
No, but to me, what you're showing is that this is not a good test.
It's not.
It's not worthless, but it's not good.
It's not worthless. It's another arrow in your supply of weapons to try and diagnose this thing. This is thermodynamics, and actually I think the way to go is kinetics, to look at time scales that things are stable or unstable. And I think the differences would be bigger then. That's just a lot more complicated to do, and the theory hasn't been developed for that. I have a grad student who's thinking about it, but he's just started. And I think with timescales, there may be much bigger disparities between the Earth and Mars, but that means developing a whole theory and a whole new metrics. This one was easy. I knew how to do this. Something else that came from the Galileo spectral imaging of the Earth. This is a false color image of South America. But the image in false color reveals a red-absorbing pigment, chlorophyll, which is not seen elsewhere in the solar system. And if you look in the spectra, so this is 0.6, so the visible to near infrared, you'll see this absorption in the red, and then reflectance above this steep line here at about 700 nanometers, 0.7 microns. This is called the red edge, where the chlorophyll is absorbing in the red and doesn't absorb so much in the infrared, at least by a factor of 2. People have suggested that you could look for this sign of chlorophyll on other planets, but of course you'd need the spatial resolution, because this is looking down on South America, and if you had everything integrated, then you'd have a lot of ocean, which you don't really see much chlorophyll there. So this would be a very muted signal. And also, why should other life have the same pigment molecule? They'll probably have pigments, but they could be other things.
Why can't we see chlorophyll in the oceans? Because there is a lot in some areas.
Well, you can in detail, okay, but it's not such a strong signal as taking the whole of the Andes or the whole of the Amazon, which is very green. But you can see it in detail in the oceans. It's just, imagine, but a lot of the oceans out here are deserts. So most of the ocean is desert. And just around the coast, if you went to the upwelling regions of Peru or something, then you'll see a lot of productivity, a lot of chlorophyll.
Oh, so
But
you can detect those.
you can detect those, but elsewhere, there's virtually nothing.
Yeah, it varies.
Yeah.
It's mosaic.
It's mostly around the coast, so it's a narrow strip around the coast where there are nutrients, and not most of it. That's the problem. And if you integrate over the disk, then you'll see most of it rather than narrow strips.
Okay, but these are detectable.
Yeah, it's used by satellites to map chlorophyll in the ocean. So, to summarize then, for an Earth-like life, we can look for evidence of oxygen. We can look in reflected light to see if a planet has an atmosphere or a surface which has liquid water with an appropriate surface temperature. And we can look for biological activity with other gases, such as methane, represented by a cow here, but anyway. And we want to try to rule out abiotic explanation. So it's not any one piece of evidence. We need to take everything together. It's the right surface temperature for liquid water. We find some oxygen. These things together are much stronger than just one piece of information. This is another diagram which says the same thing, but does it as a function of wavelength. This is from Sarah Seeger. Blueness of the sky measures the Rayleigh scattering, can tell you something about the amount of atmosphere. Ozone, maybe you could see the vegetation, red edge. carbon dioxide could be related to life, could be volcanic, methane, could be anaerobic microbes. So, my last few slides are on the idea of future concepts to look at spectra of atmospheres. This is very difficult with ground-based telescopes, even with adaptive optics, because you have to look through the Earth's atmosphere, which is already full of the kind of biosignatures you're looking for. So really, you need space-based telescopes. And there are two basic ideas with transiting planets. When it's in front, you can see transmission of the starlight through the atmosphere, so transit transmission or absorption spectroscopy. You could also subtract the spectrum of the star when the planet is passed by to try to give you more of a differential signal of the planet's atmosphere. Or you can do secondary transit spectroscopy when the planet goes behind. Here's the combined spectrum, here's the eclipse spectrum. This one minus this one equals this one. And this one is just the thermal emission spectrum, so the heat spectrum of the planet. And this has been used already by the Spitzer, which is an infrared telescope, to look at hot Jupiter's spectra. What's happening soon? The James Webb Space Telescope. Here's the primary mirror, here's the Hubble mirror, here's a human being. And so 6.5 meters telescope successor to Hubble, 2018 launch. And in principle, can measure secondary transit spectra, and in principle, might be able to measure a spectrum from a planet in the habitable zone of a nearby M star. Future concepts are things like terrestrial planet finder. So in the infrared, you need an interferometer, so you need these free-flying telescopes in space. They need a very precise distance between them in order to have the interferometry. This free-flying formation is very difficult to get the precision, and so this is the technological challenge, basically. And the European Space Agency had something similar called the Darwin mission. And then this is the coronagraph telescope, which would act in the visible. And so here, of course, the contrast ratio was that 10 to the 10 instead of the 10 to the 7 in the infrared. So you have to have some good scheme to block out the starlight. So to summarize, then, I talked about the ideas of the habitable zone. A conventional habitable zone is a belt around a star where a planet has liquid water, and it provides a guide. So this is probably where you're going to find a habitable planet, 0.85 to 0.9 AU around a sun-like star. Is the inner edge, 1.4 to 1.7, is the outer edge. But it's only a rough guide. And the habitable zone could be much wider, as was shown on that diagram from Sarah Seeger's paper in Science last year, depending on what assumptions you make about whether the planet is resistant to a runaway greenhouse effect, or whether the planet has some other kind of atmosphere besides CO2 as a dominant greenhouse gas. And this could extend outwards, perhaps many astronomical units. I talked about biosignatures, essentially gases produced by biology, and there are practical pros and cons in looking at different parts of the spectrum, the telescope size and the technique that you use to suppress the starlight. However, overall, I think it's optimistic that the technology does exist within the next decades to look for these biosignatures in spectra and maybe even find exoplanet alien biospheres. Maybe even we find life on exoplanets before, well, we may never find life in the solar system, but it's quite possible that none of these probes going to Mars or Europa or Enceladus find any life, but we could find life on exoplanets first. And so I shall end on that optimistic note and happy to take questions.